Lunch and Learn is an MFG radio network production brought to you by GIE Media's Manufacturing Group. We highlight some of the latest innovations in manufacturing and design to help you gain insights to the newest products and technologies in the medical, aerospace, defense, and electric vehicle manufacturing industries to keep you ahead of the competition. Hello, and welcome to the latest Lunch and Learn from GIE Media's Manufacturing Group of magazines. I am Jake Kaufman, and today we are glad to be joined by Iscar as they will present on the cutting-edge applications of PCD, CPN, and ceramic cutting tools. Iscar is a full solution provider of metal cutting tool products and accessories for CNC machining. Launching hundreds of new products for machining each year, Iscar is where innovation never stops. Today we are joined by Robert Navarrete, who is the National Product Manager for Turning at Iscar USA. Robert is a seasoned expert in machining and cutting tool applications with a specialized focus on cutting tools and operations. Without further ado, Robert, the floor is yours.
Thank you for having me here today. I would like to discuss hard part turning and the tools that Iscar can provide to help customers streamline their process, become more cost effective, and improve productivity. So the tools or inserts that Iscar can help provide are PCD, CBN, and ceramic. These are application specific inserts. PCD for your non-ferrous type of materials, your aluminums, your copper, stuff like that. Your CBN, which can handle your cast iron, hardened steel, high temp alloys, and your ceramic as well that can handle those same groups, your cast iron, your hardened steels, and your high temp alloys. So one thing I do want to point out is Iscar did come out with a ceramic CBN PCD inch catalog, which is available on our website. New for 2025, over 600 new ceramic inserts, over 500 new CBN inserts, and over 200 new PCD inserts. This is in addition to our pre-existing line. So what this did is Iscar expanded our line. More grades, more edge preps, more geometries. So we have a solution to any situation that could be presented to us. So first, we're going to get into PCD. So with our Iscar PCD line. PCD, polycrystalline cubic diamond, is the highest on the Vickers hardness scale. So this is going to be our hardest piece of cutting tool. So polycrystalline cubic diamond, above PCBN and above ceramic. One thing I do like to point out is diamond a mineral composed of pure carbon. So this cannot be used on steel and cast irons, because at temperatures above 700 degrees Fahrenheit, carbon atoms react with the part of the material to form iron carbide and cause the diamond structures to collapse. So these are applications where PCD will not fit. I do like to point that out. Steel and cast iron is not applicable in PCD applications. Where this PCD does apply: aluminum, our aluminum alloys, our copper alloys, wood composites, plastic, glass, rubber, and wood. If any of the customers or industries you're working with do this type of machining or these types of materials, this is where we can plug in PCD to help them be more efficient, more cost effective, produce parts faster, provide predictability due to the PCD component. So what Iscar can provide? Iscar has 3 grades that are available for PCD. We have our ID5, which is our first choice. This is our 80-20 rule. Our ID5 is going to handle most of the applications. As you see, ID5 is a PCD medium grain. Then we offer an ID4, which is a PCD fine grain for strong uninterrupted cuts, ideal for milling operations. But keep in mind, this is something we'll plug in if ID5 doesn't fit the bill. ID5 will fit most of the applications. Then we have our ID8, which is a PCD mixed grain, used when ID5 is inadequate for turning to milling applications. This is a much bigger grain size, 3 to 25 microns. As you notice, the ID5s, less than 10 microns. The ID4 is going to be less than 1 micron. So the grain structure itself. ID5 will fit most of the applications, our 80-20 rule. So our grade map for PCD inserts. So we keep in mind continuous cut, light interrupted cut, heavy interrupted cut. When are we going to apply which grade to which application? Our ID5 and ID8 are going to be able to handle your continuous cuts and your light interrupted cuts. If for some reason an ID5, which is our first choice, and an ID8 can't handle those situations, that's when we'll plug in an ID4. These are available, but our first choice will be an ID5. This is a medium grain PCD insert for continuous and light interrupted cuts. So what sets us apart and what we bring to the table, new to the market, are chip breakers on our PCD inserts. So a chip breaker formed directly on the PCD. So the fact that we're able to break chips, which was typically a type of insert which will have a hone or a TLAN, we're actually plugging in chip formers now. So we have an MD chip former, PCD with a chip breaker, and we have an RD chip former on the PCD. The corner radiuses we have available are 18 and 16 thousandths. So the fact that we're able to break chips in a non-ferrous environment is a win-win for everybody. If you're familiar with non-ferrous type materials or even plastics where it's a bird's nest, no matter what you do, bumping up speed, SFM, increasing feed rates, blasting coolant flow, all the things we try to do to get some type of chip control, oscillating the spindle, putting a dwell, we're adding a chip former, which is going to help you break chips. An example of this situation, a chip breaker versus a non-chip breaker. It makes a huge difference, especially in non-ferrous type environments. As you can see on the left, no chip breaker. On the right, chip breaker. Same grade, same radius, chip breaker, no chip breaker. Massive difference. So if you're familiar with non-ferrous type work and that's the environment you work in, and you're seeing bird nests in your chip bin, we have a solution for that. One thing to keep in mind, and we do present to customers or ask customers when they're transitioning from carbide to a PCD, is what type of RPM capability do we have on this machine? Non-ferrous materials spin fast to begin with. Now we're applying PCD, which is a much harder component than carbide. We're going to spin at higher velocities. So I think something we like to point out in a graph we do show to customers quite often. So for your aluminum alloys, depending on the type of group you're in, for semi-finishing and finishing, we could be just below 10,000 SFM. So things we like to ask, but we can also be at the lower end of the spectrum. So as long as we have that range capability for what you're doing, these tools can fly. So your aluminum, which contains above 12% silicon, you're going to be a little slower, 2,900, just below 3,000 SFM. So things we like to point out to customers, hey, we have these tools, but we want to make sure that we're not overworking the machine. We have the RPM capability. A secondary chart, and you can see the materials that are applicable to PCD on the left column, your copper alloys, your bronze, your brass, tinfoil copper, your zinc alloys, magnesium, the type of range and type of parameters you can expect to run these tools at. Just going down towards closer to the bottom, your glass, your plastic materials, your ceramic, your graphite, these are flying compared to carbide and very predictable. Very predictable. You get the high velocity, and then plus if we plug in the chip formers, you're getting high velocity plus breaking chips. So a potential great choice for your non-ferrous environment. So some examples of stuff we've seen out in the field. These are published test reports. So as you can see, aluminum, your cast alloy, the ID5 grade, it was with a GIDA, so it's a grooving tool, just under 2,500 SFM, 4 IPR, 8 thou depth of cut. The number of pieces compared to the competitor. We're just under 2,000. The competitor was just above 1,000. Your aluminum cast alloy, bottom right, ID5. Now we're using a VCGT. So a 332, 9,400 SFM, 18 inches per rev, 40 thou depth of cut, just under 10,000 pieces. Customers roughly around 6,000 pieces. So these are with our ID5 grade, our 80/20 rule grade that will fit most applications. Then we have our copper alloys in your bottom left, your aluminum magnesium, Same, best with the ID5. As you notice with the copper alloy, we're about 1,000 SFM, and the aluminum magnesium, 8,200 SFM. So just note the number of pieces different. And also, that's something I like to point out. These test reports are with standard edge preps. These are not with the chip formers. We can expect tool life to increase with the chip formers. These are standard edge preps, a T-land. So that's our PCD offering. A quick, 40,000 foot view, a quick overview. But Iscar, we do offer PCD for your non-ferrous environment. If these are application specific, where we can plug in and help customers be more productive. So hard part turning machining. So typically PCBN and ceramic inserts. These are what we are going to apply for hard part turning. Once it goes above 45 Rockwell, we're entering the world of ceramics and CBN, where these tools are going to shine. Anything below that's too soft, we're not going to be plugging in those CBN and ceramics. That's the world of carbide. So your main two types of inserts for hardened steel and high temp alloys will be ceramics, CBN, including the cast iron group. So Iscar CBN line. So polycrystalline cubic diamond nitride. So now we're a step below on the Vickers hardness scale from PCD now. So it's PCBN, also known as CBN. You can hear it two different ways in the industry, PCBN and CBN. So the industries where these are applied, and this is just a small group, there's many others: shafts, gears, pump parts, bearings, die molds, high-speed steel, hydraulic components, and printing rolls. These are industries where they're typically hardened above 50 Rockwell, and this is where we can apply CBN. So CBN inserts are generally used for finishing process. We can use CBN for roughing, but typically people will apply these for finishing process. What a lot of people don't realize is you can get a very, very high finish with CBN, potentially bypassing having to send these out for grinding. You can get an RA of 16 or better, always using a fine grained CBN. We have customers hitting an 8 finish or better with CBN. Obviously, we're having to adjust SFMs, depths of cuts, and feed rates, just as you would with carbide, but you can hit 16 or better. We have customers hitting 8 or better with a fine-grained CBN. So the coarser the CBN, the tougher the CBN, just as you would with carbide. You have your hard carbide and you have your tough carbide. Same applies to your CBN. You have your fine grain, which is going to be hard, and you have your coarse grain, which is going to be tough. So for Iscar, how that applies, we have our hard carbide, our hard CBN, I should say, which is on the left, and then your tough CBN, which is on the right. How designation-wise or grade-wise, the lower the number, the harder the CBN, the bigger the number, the tougher the CBN. You can use CBN for interrupted cut. We have CBN with the brazed wafers, we have solid top CBNs, and we have full solid CBNs. There are plenty of customers that do a lot of interrupted cut, intermittent cut, going through micro stamps with CBN. CBNs are very tough. We just need to make sure we have the correct grade and the correct edge prep for the application. And if we're doing finishing work, then we go with the fine edge prep and a hard piece of CBN. We have CBN grades and edge preps that will apply to each situation. So speaking of edge preps, so we will offer different variances. So for example, we have an S, which is a chamfer and a home. We have an E with a home, a T with a chamfer, and then a P with a double bevel. So how that breaks down is, for the example on the bottom, you have an S0420. That's going to be a 4,000 T-land with a 20-degree angle. So it's very easy to read. We also offer metric and imperial versions of this. So you have your standard edge preps, and then we also have semi-standard edge preps or chip formers, and your semi-standard. So depending on what we're applying, we have your, I'll head back, your off the shelf, your standard, And then we also ask for semi-standard low cutting forces and strong edge preparation. So metric and imperial. So this is a snapshot out of our imperial catalog. So depending on what we're doing, say we have an application, hey, we're popping chips, it's curling a little too wide or potentially curling a little too narrow, we can adjust an LS, an S, an LE, depending on what we're looking at. Same thought process as carbide. Hey, we need a more blunt edge, we need a sharper edge, we need a more high positive. Same thought process with edge preps with CBNs. So I keep speaking of edge preps, CBNs with chip breakers. This is something Iscar excels in. We have CBNs with chip breakers. We have an F, we have for finishing, an M for medium, an R for roughing. One thing I do like to point out with CBNs, with your brazed tips in this fashion, the edge prep is by application. This does not apply to the depth of cut as it would with a piece of carbide. You get a piece of carbide and say, hey, I have a finishing edge prep. You're going to take a light depth of cut. You get a piece of carbide with a roughing edge prep. You're going to take a much larger depth of cut. For CBN, this applies to the application, not the depth of cut. You're still limited by the wafer. So if you have scale, crust, interrupted cut, you might use a roughing edge prep. If we're taking a light depth of cut, trying to achieve a 16 or better finish, we use a finishing edge prep. So just an example, just like with the PCD, no chip breaker versus chip breaker, night and day. So we got your bird's nest. We walk into plenty of shops, chip bins, huge bird's nest. Plug in a chip breaker, we're breaking chips. Chips are getting out of the way. We're not recutting chips. We're not rubbing. Much better finish. So if we can apply chip breakers to your hard part turning and your high temp alloys, it just makes it a better situation for everybody. Better chip control. So chip bins are not having to deal with bird's nest. Quality, they're not worried about what's going on. Everybody's not being safe, having to put on gloves, stuff like that. We want to break chips. So that last video is dry. So people will ask, okay, do we run coolant or do we not run coolant? So wet cutting improves tool life for clean, continuous cut. Just as we just said, same thought process, same ideology as you would apply to like carbide. We have instances where, hey, we're not getting great tool life. Let's shut off the coolant. Same thing can apply to CBN. But for CBN, for wet cutting, improves tool life for continuous cuts. So we want to put the coolant on for clean, continuous cuts. For interrupted cut, we want to leave the coolant off. We're going to improve the tool life. One thing I do like to point out, and this can apply to CBN, ceramics, actually carbide, anything else. Anytime we're leaving the coolant off, we're not cooling that insert as much as it would with coolant. So we got to keep in mind the screws and the clamps. These are consumable parts. That heat's getting transferred into that screw, into that clamp. So something to keep in mind, you may want to swap these out periodically. These are consumable. These are wearable parts. So if we're running dry, let's make sure we swap out those screws and swap out those clamps. So when to use coolant? Clean, continuous cut. Let's throw that coolant on. Interrupted cut, leave the coolant off. If we have air blasts, beautiful, just to get the chips out of the way. But let's leave that dry. So we also have coated CBN. It's going to add an extra thermal barrier to that insert. So it's going to be protected. We're going to be protected from the heat. We're going to get better tool life. Just so if we have a clean continuous cut situation, or where a lot of heat's being applied, or we want to run it dry, let's leave we can run a coated insert and get extended tool life. So we do have PVD coated inserts on CBN. And with the coating grades, as you'll see, so BI05HC, that C tells me it's a coated grade. So H for hardened steel, C coated. So an example, this is a test report a test we did against a competitor. So it's our BI30H. So for hardened steel, the cutting speed was 230 SFM. We bumped up our feed rate, our IPR, to 4.5 IPR compared to 3. The depth of cut was 8 thou. The tool life was 21.7 life in feet compared to the 10 feet. So we got 2 times longer tool life. So that was our CNGA 431 2MT, so two edges, BI30H, versus another CNGA 431, extended tool life. Another report, so Iscar versus a competitor, BI30H again. This time we're in nickel chromium case hardening steel, 460 SFM, just under 4 IPR, depth of cut of 8 thou. We had 130 pieces compared to the competitor's 30 pieces, 4 times longer tool life. And this is a TNGA, so the 3MT, so that's going to be three edges, so 3MT. And that was a nickel chromium case hardening steel. So that's our CBN. It's that 40,000 foot view, quick overview. Now we have our ceramic line. So the Iscar ceramic line. So just a very quick overview, our grades overview, our offering. This is the new product offering. Iscar has 15 new grades: your aluminum oxide, your silicon nitride, your Cylon, your Whisker, and Bidemics. Typically, these will apply to aerospace, automotive, and the steel industries. So I like to put this chart up in customer seminars. Anytime I do a presentation like this, a breakdown of the grades and what groups they apply to, and they're listed top to bottom. So your Cylon, for example, on the bottom left, top to bottom, from hard to tough. So numerically, your IS-14 is going to be your hardest piece of Cylon for super alloys, and your IS-55 is going to be your toughest piece of Cylon for super alloys. And same applies across the road. So I like to show this to customers, distributors, salesmen, anybody I'm working with, saying, hey, here's our hard to tough chart for ceramics per alloy group. So won't jump into this too much, but how we are our nomenclature. So CNGA 432, WL, we do offer ceramics with the wiper. We do offer ceramics with the chip breaker. So if it had an AG, it would be a chip breaker. Same thought process as far as the fifth station or fourth stations. It could have an S for a chamfer and a rounded hone, an E for a hone, a T for a chamfer, and a P for a double bevel, chamfer plus rounded. So T0420. So your 04 is going to be a 4 thou by 20 degrees. And then you have your IS, which means Iscar Cylon, grades 45. And if it has a C, it's going to be a coated insert. So we have a massive line of edge preps. And if you're familiar with ceramics, edge preps can make or break an operation. 2 degrees, 4 degrees, 20, 4 thou, 2 thou, 20 degrees, 30 degrees makes a huge difference on chip control. So aerospace, a lot of aerospace companies use ceramics. A lot of the components that are forged have a lot of material that has to come off. Running carbide, you could be taking multiple shifts to do what a ceramic can do in one shift. Some of the typical parts we'll see out that will apply to ceramics: your fan casings, your low pressure compressors, combustion case, turbine casing, any heat resistant super alloy like your Inconels, your Waspaloys, your Renays, your Hastelloys, stuff like that. So these are alloy groups anywhere from 33 to 35, depending on what we're looking at: Whisker, Cylon, Bidemics. Those material groups, those high temperature alloy groups are where ceramics can apply. So Inconel 718, kind of like the industry baseline threshold for high temp alloys. So Inconel 718 at an operating temperature of 800 degrees Celsius is where that curve from carbide to ceramic hits. Once you hit that 800 degrees Celsius, carbide drastically fails. So, but ceramic will continue to hold strong. So ceramics maintain their flexural strength at high temperatures. Once we get over that 800 degrees Celsius, it gets hot. There'll be some downward turn for the ceramic, but we're at operating temperatures now. We want to see those chits popping off those parts. So what we just seen from left to right, your carbide, your bidemics, your Cylon, and your whisker. Your conventional carbide, 718, depending on the type of machine, I understand. So that's 35 meters per second. So roughly, I mean, we're talking 35 times 3.3, 105 SFM roughly. We're not machining very fast. These are carbide operating temperatures, depending on the carbide grade you're using. Bidemics, Stylons, and your whiskers fly in high temperature alloys. I mean, we're talking 4 times the speed compared to carbide typically. And that's just for your Cylons or your whiskers. If we throw in the bidemics, we're talking 6 times, 7 times faster. So, for example, right here, this is still metric. This is a metric conversion, but your cutting speeds and turning. So 250 meters per minute compared to your carbide, your 40. We're about 4 times faster chip metal removal rate with ceramics compared to carbide. For milling, we have this chart for milling. If milling, which will apply much more heat, so I do like to tell people to keep that in mind. There's a lot more heat put into that part in milling, but 17 times faster. So if you have a milling application that you could potentially apply ceramics for a high temperature alloy, you can remove material 17 times faster than carbide. The automotive industry, your cast iron applications, ceramics work very well. So Iscar offers an IS-26. So the IS-26 can be used both dry and wet in your turning and milling application. And said numerically, depending on what we're doing, we have an IN-18, which is for finishing. And then if we're getting into roughing or scale or interrupted cut, your IS-45. So your IS-26 is going to be your middle of the road. IN-18, smaller number, harder piece of ceramic. And then we have your IS-45, coated and uncoated, which is going to be your tougher piece of ceramic. So just an example. So 600 meters per minute. So 3 times 3, 6, 12, 18. So we're about 1900 SFM roughly on your gray cast iron. So ceramic can get rid of material very quickly. Ceramic is tough. Ceramic can be hard. Just depends on what we're doing. So now we're looking at a scaled information, your cast iron, your ductile cast iron. This is your IS-45C, so coated, flying through. So if you're using carbide for your cast irons right now, and you're roughing with it, we have ceramics that can be applied to your clean continuous or your roughing, your scale, your interrupted cut, your micro stamps. We have ceramics that can do it. An example of your operating range is depending on what you're doing. It's just a little quick cheat sheet. This is information we have in our new catalog, but I like to just plug this stuff in so customers, distributors, salesmen can see. Your gray cast iron, middle of the road for turning and milling, 27, so 2800 SFM. For your turning application for finishing, 1800 SFM. Your ductile cast iron, we're talking about 1640. Nice middle of the road. And typically dry or wet. The feed rate or depth of cut are influenced by the geometry, so we're just keeping the SFM on there because if we have a CNGA or if we're using a round, that'll influence your depth of cut and your feed rate. So ceramic tools for hard turning. So you have your automotive, your steel industry, your mill roll stuff, your gear, your shaft gear, your crankshaft, and your bearing work. Your ceramic for automotive. So Iscar offers your IN-16, said numerically, your IN-16 is going to be closer to the threshold, higher on the wear resistance, close to CBN. So if we're in a situation where CBN and we might be on that threshold of 50 Rockwell, 55 Rockwell, IN-16 may be a potential solution if we're trying to bridge that gap. CBN is not cheap. If you're looking to be more cost effective and it might not need a pristine 8 finish and it's maybe something like a 32 where we can get by with a ceramic, IN-16 could be a potential choice for clean continuous cuts. So something you can take into consideration. So the advantages of ceramics, this applies to all companies, your CBN, your ceramics, and your carbide. Price, CBN is much more costly than you have your ceramics and your carbide. But something to keep in mind as far as when am I going to apply which to which avenue. So insert must be 3 times harder than the work material. That's why we have those thresholds of, hey, 45 Rockwell for carbide, anything above ceramics, so 45 to 55, that range for ceramics, and then anything above, you have your 50 to and above for CBN. So things we take into consideration when we're looking at applications. We're not just going to plug in a CBN because, hey, we got this CBN that's going to go 1600 SFM. Let's see what's more cost effective and let's see what makes sense for your application. Because, hey, maybe we don't want to go 1600 SFM. Maybe we can plug in a ceramic at 800 SFM and hit your 16 or 32 finish with a hard piece of ceramic. Or we need that 8 finish. We need to get these parts off the machine faster because the shop rate's at a certain rate where that CBN, that rate, the feed rates we can go, the SFMs we can go, balance everything out. So stuff we take into consideration when we're looking at applications. So that was a quick overview. PCD, CBN, and ceramics. Great tools, application specific. We have your non-ferrous for your PCD, that whole alloy group. Then we have your CBN and ceramics, which are going to be applied to cast iron, high temp alloys, hardened steel. If you have any questions or any applications you want us to look at, please feel free to reach out to your sales team.
Awesome. Well, thank you so much, Robert, for that presentation. And we do have time for a few questions, and we were able to get a few in already from the audience. Kevin would like to know so far, what mix of hard turning do you see with CBN is 1-pass versus 2-pass process?
So the mixture will really depend on the geometry of the parts or the instances we do see it if it's like a larger diameter, low pressure turbine engine component when they have to do gauge passes. So it really depends on the part. CBNs are very consistent. They're very hard. So as long as you're within the depth of cut range, you can typically take it in a single shot.
Okay. And then Kevin also wants to know, is there a tolerance or CPK requirement that would steer you to use either 1-pass or 2-pass?
Not necessarily. I said CBNs, like in the Swiss world, stuff like that. I mean, easily hit plus or minus half a thou. I mean, that's just an easy target.
Awesome. Also, Robert, looks like Danny wants to know, how small of a corner radius can you make with the chip breaker? The material that he's going to be using is platinum iridium.
So off the shelf, it would be a 16 thou radius with the chip former off the shelf.
Okay. Let's see. Also, what is the most ideal for a small diameter ID boring on a thick walled 304 stainless steel at a 0.0005 tolerance?
So we didn't talk about it today.
Mm-hmm.
That would be, I would steer more towards CERMET for that application, not a CBN or a ceramic. That'd be a CERMET application, in my opinion. A coated CERMET.
Well, yeah, if there are any more questions, obviously Robert is here to answer, but obviously it was a very informative presentation. So it looks like we do have, one more coming in. So we do have, no, Kevin just saying thank you for your expertise as well. So obviously, like I said, Robert, very informative presentation, and I appreciate you taking the time today. Obviously, you were talking about your travel, so I definitely appreciate that you were able to sign on with us for a few. So massive thank you to the whole team at Iscar, and obviously a massive thank you to you, Robert. Thank you so much for your time today, and I hope you have a great rest of your day.
All right. Thank you very much. Thank you for having me.
You can listen to all of our episodes of Manufacturing Matters and Lunch and Learn podcast from the MFG Radio Network on Spotify, Apple Music, and on our websites, todaysmedicaldevelopments.com, aerospacemanufacturinganddesign.com, defenseandmunitions.com, and evdesignandmanufacturing.com.